trying to implement a Vitergi decoder, Charles coded modulation, and then try to come up with some form of partitioning for Rayleigh channels. Okay, so the overview, I'm going to talk a little bit again about modulation, different channel, my mapping, and then how I use the mapping of partition design. And then Satish is going to talk about Charles coded modulation, and then Tyler is going to talk about the implementation of our 8X. Okay, so really modulation itself is we're taking like bits, information, and we're trying to send it through an RF channel. For 8X, what that is it's QPSK over 4 discrete time intervals, which then so every time interval would have a real and imaginary component would correspond to 2 different coordinates. So you concatenate the coordinates together, and then you have 8 of them. So that's why you do it 4 times. And basically, the idea is we took, Dr. B took, she took a 2D from Saha, and she used the Cartesian product to increase the dimensionality from 2 to 4, then to 8, and also took a rotated version from Cartwright, and and took that and did the same process to get an 8D. Two 8D constellations and then union them together. And then the whole idea, the reason for doing that is to add redundancy, because you need now 2 to the 9 bits rather than 2 to the 8. So, so this is more or less this is a curve that compares our X8 coded versus uncoded. Did I put a typo? Yeah, there's a typo. The green is uncoded, and the sign, or whatever you're going to call it, is coded. And then the blue curve is the theoretical QPSK. So the idea of why the lighter green, whatever you want to call it, is above the theoretical curve is because of nearest neighbors, and it corresponds to Fournier's rule, which is depending. And Dr. B quoted in her thesis a loss of 0.36 decibels, but more than likely it's closer to 0.4, and that's as you go to infinity with signal to noise ratio. So it's as you go that way. And the idea is because when you are in 8D space, you have more closest nearest neighbors to a corresponding point, which then adds more likelihood of confusion, which degrades your performance.
Question. Can you explain a bit about the theoretical bit error rate curve, how that's obtained and compared with the experimental?
How do you get it? Well, more or less, this is just generated by the Simulink BR toolbox. That's how it's gotten. And what we did is just made like a Simulink model that has that is X8 uncoded. So in theory, there is no redundancy added. So you just have the 8 coordinates. And then this is the performance of what Tyler and Satish actually built with the constellation that Dr. B already made. But the darker or the lighter green is for just the ones constellation, the Saha constellation. Does that make any sense? Okay, hopefully. So I don't know if I can explain. I mean, the blue solid line is like automatically generated, so it's not like we had to do anything to it. But I mean, we have in the past made. I know I made a band pass and base band of QPSK. So okay, so I'm just going to talk a little bit again about the different channels. White additive Gaussian noise. Usually that's generated by thermal processes, so it's always around us. It's there. It is a Gaussian normal distribution, and generally it's infinite bandwidth, and therefore it has, in theoretic, infinite power. So, and generally NO denotes the power spectrum density. So if you had a band-limited channel, you can be able to calculate how much the power of the noise based off of NO times the bandwidth. And then Rayleigh fading There's has two components. You have the multiplicable part and the which is the small scaling and the large scaling. And the multiplicable part is caused by it's caused by it's what happens is the RF signal goes in and it has like a time delay between the receiver. What is it? It's diffraction. So you have diffraction of the signal, and what that does is it causes constructive and destructive interference with the signal, and that causes like phase shifts. And the slow and fast fading, and that has to do with the fact that you have a band response of the channel, which is causing a keying in a sense of the signal. So you're turning it's pretty much it's causing time leakages and frequency leakages. And the Doppler shift is caused by because you might have like a transmitter that's moving relative to your receiver. And the only thing really to say about large scale fading is like shadowing, which is like if you had a large mountain and you're transmitting RF, and you'd have like a shadow effect where within the mountain you wouldn't be able to actually get any of the signal. So that's more or less what that is all about. And then just little constellations of these are QPSK. This one's additive white Gaussian noise, a mixture of both, and then Rayleigh fading. And you can see how the different effects. And with this one, we actually took out the phase, and that's why it has a constant phase practically. And the speed in which these points move up and down is depending on the if it's slow or fast fading. So.
Can you explain a little bit about this signal constellation and how the fading effect come into play on these three different plots?
You mean this is just a regular QPSK. I just took it for one. What do you mean?
Well, these dots correspond to what? Like
They correspond to where the point has been moved based off of the channel response. So if there's like additive white Gaussian noise, they're going to move around randomly within it because you're just adding something to it. So if it's like 1, if it's 1 and you add to the coordinate like 1, then it'll go to 2. Something to do with that. It's just you're adding something to it.
but without any noise, where should these dots look?
I mean, I think it's like it should be somewhere around here. I'm just more or less
And for all these three different plots, they all should
be in the same.
somewhere at the same spot around.
Yeah.
I don't know about the exact coordinates. But
Yeah, I mean, I use the same scheme.
Okay.
So it's just more or less just to show what it does, more or less. The points themselves, but you can tell just by where the blob is that more or less it's like right in here. But I just took it from just one of the ones I did just to show what it does to the constellation and why it's important to, when I start talking about the partitioning, why it's important to partition it in a certain way in order to eliminate some of these effects. So that's just more or less, I hope does it explain your question really, or?
Yeah, I think so. But it would be nice that you also highlight where are the original signal constellations without
sure.
noise.
It's like negative root 2, and then like root 2, and then negative root 2, root
Like
2.
I think it's like square root, maybe square root 2, something like that.
Okay.
If you broke up the response, the points post response, you broke them up into several quadrants and take the mean, because it's Gaussian distribution, you would actually get the point.
What happened there, but I think just for the sake of the audience, it would be nice to explain about some points.
Okay. Hopefully I somewhat.
Thanks.
Okay, so what I did with how to design my partition, knowing that those effects are going to happen. Generally, for a lower signal to noise ratio, you have more or less the white Gaussian noise is going to play more of an effect. But for higher signal to noise ratio, and depending on the different environment, you're going to have Rayleigh effects. So if you do low, if you're sending something from ground station to the orbit, you're going to have more or less white Gaussian noise. But if you're sending like the city, like New Orleans here, you might have more inclining to have Rayleigh fading because of the buildings and how they interfere. So my first idea is what I did is I took a sphere and I partitioned it into hemispheres, more or less, and then did my best to gray code the hemispheres based off of how close they are. So minimum Euclidean distance would equate to minimum Hamming distance, which is more or less what you want to do. The only problem is because they were close together, the performance wasn't really good. So me and Milton more or less came up with me, Milton, and Dr. B came up with another idea where she more or less said, why don't you like tree it out? And she wanted me to maximize the Euclidean distance of the constellation. So that's more or less what I did. What I did is I have an algorithm in MATLAB script that what it does is it takes the 512 points and kind of clusters and gray codes effectively into 4 big chunks, and then takes each individual chunk and clusters again 4 times, and then so I'd have in each of those clumps 32 points, and then it'd cluster it again 4 times. So I'd have something like this. So I'd have an 8x8 matrix. These are where the rows indicate the different signals. So row 1 would be signal 1, and so on and so forth. And my logic to this is, if this is minimized, and I want to maximize Euclidean distance, that means if I'd make 8 subsets or 8 partitions, however you want to say it, and this way puts different terminology, like families and subfamilies and all that stuff, but for the sake of really simplification, you could say that in actuality, that's more or less what I'm doing. I'm making a family and then turning it into or making a subfamily that turns into a family that turns into something. But for the sake of really simplification of language, more or less, I know if these are all minimum, and if in theory, if my k-means work the way it's supposed to, then these are all minimum. Therefore, signal 1, signal 2, signal 3 to 8 should be in all separate different partitions. And I started with that assumption. And I also made the assumption from that original large initial cluster I made of 4, that, for example, I say it was P2. So I had P1, P2, P3. So there's no point in me comparing P2 to P2. So I pretty much, for the simplification of my algorithm and such, I took P2 cluster 1 and compared it to P1's cluster 1 and so on and so forth. And I pretty much sorted it that way. And then after I sorted it, I sort of quantified. So from here, next I would get is I would have 8 groups I'd have 8 effective running total partitions. So I have 8 running partitions with 4 signals in each of them based off of my comparisons. And then what I did is I quantify that effectively into a centroid, because I figured the best idea would be to sort of have the overall effect of this new running total partition compared to other running total partitions and see which ones should go together. So I'd have partition 1. So I went from 64 of these matrices down to a little bit more, and that's basically the logic for how I brought it together. Is I took this from this tree, I took these, and I said which ones. I took the running total partitions, because I would have multiple of them. I'd probably have 64 of them or more, and say which one of these are very close together respective to each other through the means of clustering, which was really good, because what that does is it simplifies it back down to an 8x8 matrix. So I could just run iteratively more or less the same code. So that's more or less what I did. And also I figured you can make the argument that cluster 1 might be better with cluster 2, but I figured eventually in the long run, if that's the case, then they would all come together eventually. And then so that's what I did. I made 8 partitions, and it wouldn't be that difficult to take those 8 partitions and make them 4 if I had to. And so I wrote a little function that made them 8, and they pretty much coded them for the trellis in their system. So because you have a special coupling between which partition should be which states in effect, and I assumed that coupling to be, if I had 2 clusters and I find where the Euclidean distance are maximized, then those should be coupled together because they're less likely to be confused partitionally wise. So that's more or less what I did. But after this, the real trick is to take that long list of 64 points or whatever and somehow gray code it. So I used something really simple. I just k-meansed it and sorted based off of, and I iterated that a few times just to sort it where the points that were, it should be in the same clustering in a sense, should be all together effectively. So that made the most sense. And then I had put a running gray code list next to it and then sorted that way. So you could just index the partition easily and assuming that's the gray code value. So it's a simple, stupid way of doing it, but it works, hopefully. So, and I think this is use of these. Okay.
So I pretty much did the trellis-coded modulation. A trellis-coded modulation is a combination. It combines the coding with the mapping, and its advantages over the classical way, because in the classical way they did coding and mapping separately, but in trellis-coded modulation you can directly map the encoded bits to a subset. So the trellis-coded modulation has a convolution encoder that produces trellis, which maps the subset, and then on some uncoded bits that chooses what point in the subset to be transmitted. So convolution encoder, it's a part of trellis-coded modulation that it's an error correcting code, and by coding we mean we add a redundancy to the input bit, so that it would be easier for the decoder in the receiver's end to decode the signal. And the convolution encoder has memory units that produces the trellis or the state machines, and we can see what convolution encoder we used in the later slides. So this is the convolution encoder that we used for the rate 1/2 that Dr. B uses in her dissertation. So this is the convolution encoder of rate 1/2. By 1/2 we mean one bit is coming in and it's working. So one bit is coming in and 2 bits are going out. And since there are 2 memory units, there is like 4 states. So it's going to be 0, 0, 0, 1, 2, and 3. So, and the number of output bits determine the number of partitions. So for our case, we used Dr. B's partition, Dr. B's exit partition. It's called W, X, Y, and Z, which are the set of points, set of 128 points each. We have a total of 512 points, but she broke it down to the subset of 128 points in each subset. So the way it works is, say we have the convolution encoder, the output of the convolution encoder is dependent on the input bit and the state of each of these memory units. So say we have a convolution, say we have 2 flip-flops at a state of 2, and an input bit of 0 is coming in. The output would be the present state and the input bit coming in, so the output would be 0, 0. So 0, 0 is W1. So when it is in state 2 and input is 0, the output would be W1. The output from the convolution encoder would be W1. So the next state is determined by this feedback loop. So this 0 feeds back to this flip-flop, so the next state is 0. And then the previous 1 in here is XORed with a 0 in here to produce 1 in here, so the next state is 0, 1. So we made a truth table out of that, and that's basically what the trellis is. So you have a convolution encoder at state 0, you receive the input of 0, so it goes to 0. So each transition on this trellis is the partition. So when it goes from 0 to 0, it outputs W1. When it goes from 0 to 1, it outputs X1. So that's how it works. And this is the convolution encoder of rate 2/3. Since there are 3 flip-flops, there are 8 states. And since there are 3 outputs, there are 8 different subsets. So these subsets are again from Dr. B's dissertation, and each of these are 64 by 8. I mean, that means it's 64 points in each subset. So we have a total of 512, and each of these subsets have 64 points each. So again, again the way it works is say the current state is 0, 1, 1, that is 3, and the input is 3. The output would be so 1, 1, and the output 08 would be same as the current state of this flip-flop, so it's going to be 1, 1, 1. So the output is 3, which refers to the Y subset, and then the next state again is going to be determined by this feedback loop. So this the feedback loops, this 1 goes here, and the 0 XORs with the 1 coming in to get 1, and then the 1 in the previous state, this 1 XORs with this 1 coming in to get 0 in here. So the next state is going to be 6. So the same thing is represented here. So say you are at state 3, and the input bit of and input is 3, you go to state 6 and output Y, I guess. Yeah, it's not clear in there, but so this is how this is the trellis coded modulation implementation in Simulink. So this is the convolution encoder. We used truth table for the convolution encoder, but previously we've used stateflow for that, and we can also use a built-in Simulink block. But the disadvantage of using a Simulink block is you can only output bits, so you have to use a lookup tables again to determine which subset that output refers to. But we used the truth table for this implementation. So here you cannot see 2 bits coming out, but this is 128 by 8, so that means it's a subset. So this convolution encoder is outputting a subset W, X, Y, and Z. Each are of size 128 by 8, and these points in here, the 7. So 1 bit, the last bit goes into the convolution encoder and outputs a subset, and the rest 7 bits chooses which subset, which coordinate in each subset to transmit. So from here you get a 128 by 8 matrix having 128 points, and then this from lookup table, from these points it selects which one of those 128 points are to be selected for and be transmitted later on. So this is the 2/3 implementation. You have 2 bits coming in, and then you have 8 subsets. You have 8 subsets coming out. You have one subset coming out, but since there are 8 subsets for 2/3, each of the subsets are 64 by 8. So again the last 2 bits produces a subset, and then the first 6 bits selects which point on the subset to be transmitted. And then on the receiver's end, we use Viterbi algorithm, and Tyler is going to explain what that is.
One quick question
Okay.
regarding the previous
Mhm.
slide. When you build this Simulink model, the input I assume is like the binary sequences, 1s and 0s, right?
Yeah.
And then the output is
No. The input is a random number from 1 to 8.
I'm sorry?
The input
It's a random number between 0 and 7.
7, yeah.
Okay.
Yeah.
And then the output would be what? I mean, the
Well,
output,
this would be that would be one of the signal coordinates from the partition. So it'd be either a series of 1s and -1s, or a series of 0s and square root 2s.
Twos, yeah.
Does that make sense?
when you say coordinates, that's like
The modulated.
modulated signal in some signal space. What the dimension of your signal space?
It's 8-dimensional.
8 dimensional.
So you have a
Okay.
coordinate.
And then you have the coordinate for each signal
Correct. So
within this 8-dimensional space, and you try to output that as your modulation scheme.
yes, so pretty much you get a binary sequence in that's 8, and then the convolution encoder adds redundancy to it, so that makes it 9. And
And
so
then-
also what the convolution encoder does is it outputs a particular subset into this lookup table, which is a list pretty much of all the possible coordinates within that subset, and then the rest of these indexes row-wise which one it should be, and that's what's outputted. Does that make sense? Okay. And that coordinate is 8-dimensional.
Okay, so my part was to take everything that he did and that he did and then just do it backwards, because we have to decode it. So we know these subsets. We know the subsets, and what we're going to do is going to have that on the decoder side. So what we do is we take each subset, take the received signal, and copy it a bunch of times, and do this calculation, just Euclidean distance, and then sum up. And we have then a list for each subset. We have a list of 128 distances. We find the minimum in each of those. We find the minimum of each of those in each subset. Call it W1 for the W subset, dx, dy, dz for those respective subsets. So we have 4 minimum distances, and of course for the rate 2/3 encoder we have 8 minimum distances. So we have 1 minimum distance per subset, and that is going to be the output of this branch metric unit. This is the first part of our decoder. We can then use these weights to determine probabilistic weights at each point going through a trellis, because their eventual goal is to find the path through the trellis that our encoder took, and by doing that, we can kind of weed out local mistakes, because we can see more than just one transition. We can see multiple transitions, and since each transition is dependent on the transitions before it, that gives us additional information that's going to give us the strength of our decoder. So we take whatever amount of states we have, and for each of these states, there are 2 previous possible states. For example, state 00 could have come from state 00 or state 10. So state 0 or state 2. And when the choices are state 0, 1, 2, or 3. It could have come from state 0 or it could have come from state 2. So we calculate how it could have gotten to state 0. So we take the accumulated path metric unit distance from state 00, add the distance that we find from the branch metric unit, and then we compare it to the other possibility. The minimum of those 2 possibilities is going to be our weight for state 00 at the point that we're these are from the previous points. At our current point, we look at these 2 to find out the minimum of those 2 is the most probable path to that one. And we do that for each state because we want to keep all the possible paths, all the minimum possible paths. So essentially we have 4 minimum possible paths at any given point. For our rate 2/3, it's going to be 8 possible paths. When we do this 14 times, that is our constraint length, and that is determined based on your number of subsets. States. Never mind. States. It's determined by your number of states. For us, it's 14. So, just to kind of give you all a visualized version of what I just described, this is 0. How do you get to 0? You go from here or from here. How do you get to 1? From here or from here? So we add what we have accumulated here, add W1, and then compare it to WX or DX added to here. And then we go from this point, do that again. Because imagine this is just a repeating process. Does that make sense to everyone? So for here we take the minimum of this plus R, this transition plus U, this transition plus T, this transition plus V. So that is how we accumulate our what is known as our path metric unit. And we add these together, and then once we have 14 of them, according to our constraint length, we're going to go to the next part of the process. So once we have our 14 accumulated path metrics, we start going backwards through them. We take our 14 by 4 matrix and we flip it. And if we're looking at the first one, we pick the minimum of the accumulated path metric unit because that has the most information. It has 14 it's gone through 14 transitions. Therefore, the minimum accumulated distance there is going to coincide with the minimum path at that point. And then we also use, if we're speaking recursive, in a cyclic manner, at this point when we're looking, okay, we use the most recent point of the previous 14 points to determine the transition.
Quick question. I saw you put a red dot below this 10 on the whole space. Is there any particular reason?
That's been
from
there for a couple slides.
Yeah, I think that's from the camera.
Okay.
Oh, it's from this. Look at that. Okay, cool. Let's get rid of that.
Oh,
I love that. That's neat. Okay, so then after we pick that, then we start using the backwards mapping of the convolutional encoder. We basically just have the same convolutional encoder. We just, whatever manner we create that, we just create it backwards. So we're going through picking the minimum accumulated path metric unit at each point and making that transition. Therefore, so going forward, we went from here to here, here to here, and we tried all those. So now what we're doing is going from here to the minimum of this, 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 or this. Because those are the possible transitions to get to it. Now we're trying to get back from it. We're going backwards through the trellis. So we pick each minimum, and we output the corresponding bit that went into the convolutional encoder to make that transition happen, and we output the subset that was selected for that point. So at each point, say we pick 0 to 0, this transition has an associated subset that we now know, and it also has to have an associated bit that was input to the convolutional encoder to make this transition happen. So we now know both of those things for all the points, and then we take the indices that we took from the branch metric unit. Basically, we said, okay, so these are within each subset. We have 4 minimum distances. Those 4 minimum distances each correspond to a point. We take those 4 points and we remember them for now, because now we have which subset it was. So, okay, we now know that it was W. It was from the W subset. So we pick the index corresponding to the point that had the minimum within the W subset, the difference between the W subset and the received signal, Euclidean distance wise. So we know that, so now we've used this decoder to determine what subset it was, and we remember which of the 4 possibilities it was, and we just pick based on what subset we know it is. We pick that index, and therefore we have the point. And of course, for the rate 2/3, it's between 8 subsets. So here's my example. If in state 0, 0, the minimum between PMU is, these are previous. So we're going backwards. If this is the minimum, we output subset W1 and in bit 0, because that's the reverse operation of the convolutional encoder. So future work for this implementation, we implemented the truncated Viterbi algorithm, which we took 14 points. We took imagine taking a you're just calling each point on a big scale from 1 to forever. I took 1 to 14 and made a path decision based on those 14. And then I took 15 to 28, made a path decision based on those. Future work could improve our algorithm by taking 1 to 14, making a decision, and then taking 2 to 15, making a decision, 3 to 16, making a decision. That's one improvement we could work on. And the actually, I think, in my opinion, strongest thing, improvement that we can make is generalization. There's a lot of pattern to this mapping. I mean, of course, it's mapping. Of course, it has patterns to it. So, if it has a pattern to it, it can be generalized very easily. I've actually written a script that does a naive generalization to any sized encoder and any number of sets and any number of subsets. That again could be improved so that distances are optimized and error is minimalized. But just to have a naive version is I think good. So you can create arbitrarily sized encoders and subsets. So, for example, you can get a 64-state convolutional encoder and even a 256-state convolutional encoder with the click of a few buttons. So that's something that we could look forward to improve our implementation. And the beautiful part is that once you kind of like see the pattern, all you have to do is create matrices using these patterns, and that is how you can use your selection between transitions and decoding, and it becomes very operational. Becomes actually very efficient, and it becomes very easy to type because then this creates your mapping matrices for you, and then you just input them as parameter to Simulink, and then Simulink just uses them as lookup tables, and it's very easy for MATLAB to do. Questions?
Well, I guess back to the original slide, you have the theoretical curve and the simulations. Are these simulation results corresponding to your Viterbi algorithm that you did? Or
This is QPSK. This is supposed to be QPSK, but the subsets are not optimized for on their distance metrics. So you have neighboring points that have that are easily confused with one another to have high bit error rates between them two. Like if you make a mistake between them, your bit error between the two nearest neighbors could be 3 instead of 1. We would like it to be very small.
so the bottom line is this could be potentially improved in terms of the bit error rate.
Basically the light green curve here is the uncoded APSK, uncoded XA implementation. The like blue-green cyan color is the using the coded, the Viterbi algorithm with Dr. B's partitioning with just white additive Gaussian noise. So the idea from this is more or less to take a baseline and see if it's actually working. And I know, I talked to Dr. B and she said this one is working. Or the uncoded reflects what it should be because it's like a dB derivation of like 0.5, but as it goes asymptotically to infinity, it should be around 0.4, which is, she said that it's within the range of error. And this one seems to be correct. I don't know where these go, but because we were talking with Milton, and Milton said that his was around like 2 dBs to 1 dB better. So the idea would be hopefully my partition, if I do it correctly, would lie below this, and that would be publishable. So.
Just to my curiosity, how did you obtain the bit error rate below like 10 to minus 6 in simulation?
You mean these?
Well, somewhere below 10 to minus 6.
You let it run for a few hours overnight, and that's how you can get it?
Okay, so you're talking about transmitting like 10 to the power 8 or 9 bits.
Yeah, the simulation just like keeps on doing it for us, and like I've run simulations overnight just to let it run. And that's how you can get these really nice numbers. Because once you're hitting here, you're like here's a million. So every million bits an error. And this is counting how many errors. So so pretty much it would count up to like 20 errors and do that multiple times. And it might take like a good one going down to here might take a half an hour. Down here, you're looking at like maybe overnight. So.
Yeah. These curves get smoother with the you increase the number of errors. I mean, it's just central limit theorem.
Yeah. Any more questions, Dr. Chen?
I guess I've asked enough questions.
No. As many as
Ask
you need.
away. Makes me think on my feet. Any other questions?
All right. Thank you very much.
Clear as mud?